Hello, this video will be a little bit longer. I would say I'm shooting for 15 minutes, and we left off with the Bohr model. Now, the quantum mechanical model was come up with as a way to explain all the hydrogen, all the elements beyond just hydrogen and their spectra, and why we get certain lines for each one. So Erwin Schrödinger, Louis de Broglie, a lot of physicists in the early 20th century came up with this model, and it is the current model for how we talk about electron energy levels. So there's problems with the Bohr model. It can only explain the hydrogen spectrum, and as we know, there's a lot more elements than hydrogen. There was no proof of these circular orbits. That's a very simplified model. And it didn't explain this thing called the electron collapse. So if you think about planets going around something like a sun, eventually orbits collapse. And if you were using the Bohr model, eventually you would get these electrons collapsing into the nucleus, which doesn't happen. So the big revolution here is that it treats the electron as both a particle and a wave. So that doesn't seem to make sense, because electrons up till that point were just thought of as really tiny particles. But now that we think of electrons a little bit like light, because they can travel a little bit like a wave. And the result of all the math here is something called quantum numbers. And these quantum numbers are an explanation for probability of where electrons actually lie in the atom. So there's 4 of them. You don't need to memorize them, but it's good to talk about what they mean. And they give the most probable location, sort of like an address, for where an electron is going to be in an atom. So a good analogy is where to find you on a school day, at least when we are at school. And you might say that on a typical day, you'll be on campus. And then that would be the big area. And then your sublevel might say, we'll say the H building. So you're in one of these larger buildings. And then we'll say you're in orbital, we'll say H206. Would be your classroom, and then where in that classroom would be your actual seat. So we can get more and more specific with where each electron is within that, with these 4 principal energy levels. So they're given the letters N, L, M, and S, but you don't need to know those. And our energy levels are kind of like the big areas, similar to the Bohr model. So one of the tricky parts of the quantum mechanical model is these shapes. And these shapes, or sets of shapes, are known as the sublevels. And the S sublevel is a spherical shape that goes around the nucleus. You can pretend the nucleus is right in the middle here. And then the P sublevels are a set of 3, and they are usually referred to as dumbbell shaped. The D look a little bit like a clover, or maybe a double dumbbell. And the F is a set of 7. And these, again, it's hard to say the shape of the F, but these are sets of spaces or probabilities where you're most likely to find an electron. And another tricky part is they overlap each other. So in one atom, you actually have all of these spaces overlapping each other, and different versions or different sizes of these spaces. So if you're a little bit confused, that's okay. That comes with it. As I go through these charts, feel free to speed them up. You'll see a trend. And once you see that trend, you don't have to listen to every word I say. You can skip on to the next table. But this is just a summary of the sublevels. An S sublevel is the spherical one. It's always a set of 1 orbital. And if you take nothing else out of today, remember that an orbital always holds 2 electrons max. So these orbitals, these individual shapes, can hold 2 electrons in that space. So the S is a set of 1 orbital, The p is a set of 3 orbitals. So 3 orbitals in the dumbbell shapes, each one can hold 2. So the p sublevel can hold 6. The d sublevel, you might see the trend here, is a set of 5. So if you guess 10 electrons, that's awesome. The f sublevel holds 7, or has 7 levels, and it can hold 14 electrons. Now, as we go into farther and farther energy levels in the atom, we can add more sublevels. So the first energy level holds, has just 1 sublevel, and it is an s. So the simplest one. The second one has 2 sublevels, and it gets a little repetitive. It has the 2s and the 2p. So this number in front is the energy level, and the letter is the sublevel within that energy level. The third sublevel has 3s, 3p, and 3d. And you might guess the trend here. The fourth sublevel is going to be 4s, 4p, 4f, 4d, and 4f. If we go to the fifth sublevel, you get 5s, 5p, 5d, 5f. Technically, you could have a 5g, but there's not one that exists because we start getting into elements or more electrons than are in our periodic table. So this last one turns out to be, or at least this part, is what if you have 2 electrons in the same orbital? Can you have 2 electrons on top of each other? And the explanation for this is no. You can have 2 in the same orbital, but we say that they're spinning in opposite directions, or you could think of them as orbiting in opposite ways, although that's not totally accurate. So there are 2 possible directions of spin. Electrons with an orbital within an orbital must have opposite spins. So you can think of it as like 2 magnets within this, where you'd have one oriented in the north-south direction, and then the other would be in the south-north direction. So they're flipped opposite, or you could say they're spinning in the opposite direction. If you look down here at these little arrows, when we're drawing an orbital diagram, which we will soon, we say one electron has a spin going up and one has a spin going down. So one of the scientists attributed with this explanation is Pauli, P-A-U-L-I, and he says, or his principle says, no 2 electrons can exist in exactly the same quantum state. Every electron in an atom will have a distinct set of quantum numbers. So this is a little bit repetitive, but if we look at the energy levels, our first energy level is really simple. It just has the 1s subshell with 1 orbital and 2 electrons. The second energy level will have the 2s and 2p. So that would be a total of 4 orbitals. So 1 in the s sublevel and 3 in the p. And if you have 4 orbitals, you're going to have 8 electrons, 2 max in each. For the third level, we'll have 3s, 3p, 3d. And if you see the trend here, this gets to 9, and you might recognize these numbers, the 2, 8, 18. You might have learned in middle school for how many electrons can fit in energy levels. And the fourth one is going to be 4s, 4p, 4d, 4f. So if I add all this up, 2 plus 3 plus 5 plus 7, I believe that gives us, make sure I get my math right here, 16, of course, 32 electrons. And this starts to give us a roadmap for where electrons are in an atom. So all of this is background, and now we're going to get into the, well, what do I do with this, Mr. Thomason? Well, the idea here is for any element, and we'll start with carbon, we're able to write what's called an electron configuration, or an address for where the electrons are. And part of that address is saying, well, what energy level are we in? And it always starts with 1, and it always starts with the S. So we're always going to have the same order for the most part for these atoms. And if you learn the order, you're going to get most of these right. The sublevel is shown after the energy level, so that would be like 2s, p, d, or f. And then the number of electrons in that entire sublevel, so not just the orbital, but the entire sublevel. So if you have a periodic table in front of you, that's great. If you don't, pause this video and grab it and look at carbon on your periodic table, and you should see that carbon is element number 6. So it has 6 electrons. Okay, 1 point on your quiz right there. Now, when I write the 6 electrons, I'm going to start a little repetitive here and say, well, the 1s orbital is first, and it can hold a maximum of 2 electrons. The second energy level and sublevel is the 2s, and that can hold a maximum of 2. And then the 2p can hold a maximum of 6, but since carbon only has 6 total electrons, the 2p sublevel is only going to hold 2. So this is what we call the electron configuration for carbon. And if I add up the subscripts, 2 plus 2 plus 2, that is 6, which is my total number of electrons. So make sure your superscripts, not subscripts, adds up to your total number of electrons. You can also show this using arrows, what we call an orbital diagram. So here we have the 1s, the 2s, and instead of showing the shapes here, we're just going to show lines. And so this is the 2p, this whole area. So the 1s has 2 electrons in it, an up and a down. The 2s has an electron in it, or 2 electrons, up and down. And then the 2p, we space out those electrons. Electrons are negatively charged, so they space out from each other. And we can show the electrons, instead of as a configuration or an address, we can show it a little bit more of a map or a diagram. So how did we do this for all our elements? So we start filling electrons in the subshells of the lowest or first energy level first. So that would be the 1s. And then we build up to the higher and higher energy levels. Always, always max of 2 electrons per orbital. And then remember that the subshells for S, the s orbitals hold a total of 2. The p holds a total of 6. D holds a total of 10. And F holds a total of 14. That's electrons. So for the number of orbitals, S is 1, P is 3, D is 5, and F is 7. So that's where we get the number of electrons in each sublevel. All right, a couple more things to finish up here, and then we'll do some examples. Electrons within an orbital must have opposite spins. That's the Pauli exclusion principle. So that's why we do an up arrow and a down arrow. And it's good to remember the Pauli exclusion principle, that name. Also, I'd like you to remember the Hund's rule. So if you have arrows, if you have more than one orbital, like a p sublevel, it ends up that you fill only 1 electron in each orbital before you pair them up. So don't pair them up until you've spread them out as much as possible. So if you have 4 electrons, and let's say this is a 2p orbital, the wrong way to do it, according to Hund's rule, would be like this. So you don't want to pair them up. According to Hund's rule, we do 1 at a time. And I usually do, and most chemists do, just 1 arrow side to the arrow here. And then it's kind of a half arrow. And this is the correct way according to Hund's rule. All right, so let's pick an element here. And we're going to fill what's called an Aufbau diagram, which is a little bit more complete way of looking at this. But again, we're just putting arrows for electrons. Up arrow first, down arrow second, and let's do boron first. And since boron, we're going to write the electron configuration down here. Let's first put it on here. So pause, look at your periodic table. How many electrons does boron have? Well, it looks like boron has 5 electrons. So let's put boron's 5 electrons into this energy diagram. So I'm going to start with an up arrow in the lowest energy level, lowest orbital. So I've got 2 electrons so far, 3, 4, 5. So this is the Aufbau diagram, or the orbital diagram for boron. And then if I write the address, it'll be 1s2, 2s2, 2p1. Now I'm going to erase this and do the diagram for phosphorus. I'll use a different color. Now, how many electrons does phosphorus have? I believe 15. So with 15 electrons for phosphorus, we're going to start in exactly the same place. So the lowest energy orbital is the 1s. So we'll do 1s with an up arrow and a down arrow, and then 2s, and then 2p, filling in according to Hund's rule, 1 at a time before we pair them up. We're up to 10 electrons. 12, 13, 14, 15. So that is the orbital diagram for phosphorus. If we write the address, switch to black here, you get 1s2, 2s2, 2p6, 3s2, 3p3. One last thing I want to note is that the outermost or highest energy level S and P electrons are considered the outer or the valence electrons. So because the highest energy level in boron is energy level 2, if I look at the 2s and the 2p and add up the superscripts here, it looks like there are 3 valence electrons for boron. And for phosphorus, if I look at the highest energy level, which is 3, and add up the S and P superscripts, the valence electrons for phosphorus is 5. And this is very, very important for determining how these elements are going to behave, how they react, what kind of ions they're going to become. And I went a little over 15 minutes, but try the rest of the examples. And if you have questions, jot them down and I'll answer them.